Hey there, Chem Squad. In today's lesson, you're going to learn about mass action expressions. Now, there are a couple of types of mass action expressions. One of them is called a reaction quotient, and the other one's called an equilibrium constant. We'll look at both of them briefly today, but we'll focus more on the equilibrium aspect of it. So, a mass action expression is just a ratio between the amount of products that you have and the amount of reactants that you have in a chemical reaction. So let's look at a very generic example. In the example that you see here, we have 2A plus 1B, which are our reactants. So I'm going to just write in an R for reactants to create 1C and 3D, which are your products. So I'll put a P for products. Now, because we're talking about the amount, we normally talk about amounts in terms of concentration or molarity. So we'll put these square brackets to represent the concentration of our reactants and the concentration of our products. Now, in a mass action expression, the setup is always the same. So if we want to write out a mass action expression, we always have the amount of products divided by the amount of reactants. Okay. Now, I realize that we have more than one reactant on the reactant side, and we have more than one product on the product side. So, truthfully, we'd have to show them as such. Okay, so we have to show them individually. So, when I look at my products, I have a C, substance C, and that's going to be multiplied. Now, it's multiplied, not plus. Okay, it may be plus in the reaction, but when you do the mass action expression, it's always multiplying the products and reactants. Okay, so you have C and D being multiplied divided by A times B. Okay, so that takes care of the actual substances. But you'll notice that we have coefficients in front of each substance. Okay, the ones aren't really the problem. It's any number other than 1. Okay, so if we have coefficients in front of each substance, those coefficients are now written as exponents when you write out your mass action expression. So the expression that we have up here right now is incomplete. So in order to complete the expression, we actually have to add in the correct exponents. Now, let me put the substances in first. Okay, and then we'll just go back up. There's a coefficient of 1 in front of the C. So technically there is a to the power of 1 for C. And it's to the power of 3 for D because there's a coefficient 3. For A and B, there's a coefficient 2 in front of A, so that becomes exponent 2. In B, there's a coefficient 1, so it becomes exponent 1. This is the correct mass action expression, okay, that contains products divided by reactants, and all the coefficients are now exponents. So, depending on what kind of reaction is given to you, there are typically two kinds of mass action expressions. So, we'll look at one very quickly, okay, and that's a reaction that has only one direction. So, what we're kind of used to seeing as a normal reaction. If you have a normal reaction with just one directional arrow, the mass action expression is now called a reaction quotient, and it's represented by the symbol Q. So you'll see that it's the same reaction that we have in the above. So really the only difference now is because I know that there's only one arrow, I'm going to use Q instead of mass action expression, and it's going to equal the same thing. It'll equal C to the power of 1 times D to the power of 3 over A to the power of 2 times b to the power of 1. So obviously, the ones you can basically ignore, okay? But you have to have the exponent 3 and the 2. Okay? Now, the other alternative is if you have an equilibrium reaction. At this point, the mass action expression is now called a KEQ expression. The symbol that we use is K, capital K, and then subscript EQ. Okay, so for this one, instead of Q equals our products over reactants, it's KEQ. So this time around, I'll write it out without putting the ones in for the exponents. Okay, so D, because its coefficient is 3, the exponent has to be 3, and you have to write it in. Mathematically speaking, that is the correct way of doing it. 2 has the exponent 2, but b to the power of 1 is basically just b. Okay, so this is also the correct form of our KEQ, and that's only because you have the double arrow to tell us that this reaction is at equilibrium. So therefore, this is the equilibrium expression. Okay, it's called an expression because that's all it is. It's just a formula telling you how to calculate something called KEQ. So as we continue further into this lesson, we're going to take a look at the meaning of KEQ. However, the KEQ expression has a couple of more conditions, okay, more so than the reaction quotient. So let's take a look at some of these special conditions. So the first special condition, for KEQ, we only include substances that are in aqueous state and or gas state. Okay, anything that is in solid or liquid states are basically replaced with a 1. Okay, I'll show you what this means. This time we'll use an actual example. So let's go with PbNO3 bracket 2. Okay, this is a substance that's in aqueous solution, and we're going to add potassium iodide, which is Ki. It too is an aqueous solution. Okay, since we're talking about equilibrium, we're going to have to use the double arrows. Okay, so they can look like this, okay, or they can literally just look like 2 arrows. Doesn't matter. You'll see both of these arrows being used for equilibrium. And that is going to give us a double replacement reaction. And you're going to form lead iodide, solid, okay, because it precipitates, and KNO3, aqueous. Now, with every single reaction that we now write, okay, we need to put the states in, but we also need to balance. So we have 2 iodines over here on the product side. We need 2 iodines on the reactant. So there will likely be a 2 in front of the Ki. Because we put a 2 there, we need to put a 2 in front of this K. But that gives us 2 NO3s. And when we look on the reactant side, and there's already 2 NO3s, 1 Pb, 1 Pb. It's all balanced. So if it's all balanced, it's all good. Okay. So if we were to write out the KEQ expression, okay, the equilibrium expression, it's going to be products over reactants. But remember, we only involve anything that's aqueous or gas. So in our situation, the first substance, PbI2, is a solid. Solids get replaced with a 1. so I put a 1 in. The other substance is KNO3. So I put KNO3 in brackets to show that I'm talking about the concentration. The coefficient is a 2. So now it becomes exponent 2. All of that is over PbNO3 bracket 2 times Ki. And because Ki has a coefficient 2, it becomes the exponent 2. Now, this is exactly the same thing as me writing it without that 1 there, right? Because the 1 represents the solid, the KEQ expression is literally just KNO3 to exponent 2 PbNO3 bracket 2 times Ki squared. Okay, so this is the equilibrium expression. Okay, which is KEQ. So it's important for us not to include solids and liquids only because they're so compact, okay, they're atoms. Any kind of changes to solids and liquids usually don't really affect equilibrium that much, okay? But things that affect equilibrium the most are the movement of molecules when things are in aqueous state or gas state. So that's why we include them in. So you're going to see all of this come into effect a couple classes from now. Right now, when we're learning, we're just kind of learning things bit by bit. So if it doesn't seem to make that much sense in terms of why we're doing something, okay, there's usually a reason later on. So here we have the KEQ expression, but we don't have an actual value. It's just a formula. Okay. So the second point that I want to make is we use the same symbol, okay, KEQ, to represent an expression, but we can also use it to represent a number. When it's used as a number, that expression is now called an equilibrium constant. So, example, I'm not going to be that creative. I'm just going to use the same expression that we had up at the top. So if this is our KNO3, and here's our PbNO3 2 times Ki to the power 2, okay, this is the expression. If KQ actually equals a number, then that means that we probably had numbers put in for every one of these concentration values. So if we knew their concentrations, we can actually simplify that expression into a value. So let's say that value is 2.25. Okay. If it's just a number, this is called an equilibrium constant. Okay. So equilibrium expression is what we see on the left. Equilibrium constant is what we see on the right. Okay. The constant is basically solved if we actually knew the concentrations of our products and reactants. Okay. But right now, I've just given you a number. Okay. Now, the whole thing about this is so that once we do have numbers to plug into our formula, our expression, and we arrive at a KEQ constant or equilibrium constant, what does that constant mean? What does the number mean? Well, the number tells us many things. Okay, so equilibrium constants can tell us information about how an equilibrium reaction changes. Okay, key word is how the equilibrium reaction changes. So to go through this section here, let's again go back down to something a little bit more simplistic and generic. So we have an equilibrium reaction here between reactants and products. So reactants are going to be big R, products are just going to be big P. Okay, so suppose KEQ is greater than 1. Okay, what this means is KEQ always equals our products over our reactants. But we're saying that KEQ is greater than 1. Okay. Well, in order for it to be greater than 1, the products has to be a larger number. Okay, so let's say the product is 10 and the reactant is 5. Okay, better yet, I'll keep the same numbers, but I'll put in a unit. Let's say the products here are 10 molarity in concentration, and the reactants combined were 5 molarity in concentration. Okay, 10 divided by 5 gives you 2. Molarities cancel out, so this is just a number. So KEQ right now is greater than 2. So what does that mean? Well, it meant that you had more products than reactants at equilibrium. So it means we have more products than reactants at equilibrium. Okay, so between reactants and products, okay, the reaction is actually leading more towards the product side as it goes to equilibrium than it did with the reactants. So this forward arrow is much bigger than the reverse arrow. But by the time the two arrows balance out, okay, by the time the rates balance out, you just have more products than reactants at equilibrium. That's what a KEQ greater than 1 means. So if we apply this same understanding then, okay, the same concept, in order for KEQ to be less than 1, okay, the number at the bottom has to be bigger than the number at the top. So you had to have a smaller amount of products and much larger amount of reactants at equilibrium. So more reactants less product at equilibrium. Okay, that's what a KEQ less than 1 means. So just to summarize the two, if KEQ is bigger than 1, it means that you have more products than reactants at equilibrium. And if KEQ is less than 1, you have more reactants and less products at equilibrium. So how can KEQ both, what would it mean if KEQ equals 1, like exactly 1? Well, in order for that to work, both the numerator and denominator have to be the same number. So if KEQ equals 1, the products and the reactants have to be equal. So both must be equal in concentration at equilibrium, or when equilibrium is reached. Okay, so you have the same amount of both. And then finally, what happens if KEQ is equal to 0? Well, in order for KEQ to be 0, that is, in order for this ratio of products divided by reactants to be 0, the products have to be 0. So products must be 0 at equilibrium. So what this means is you have no products when equilibrium is reached. Okay? If there's no products, it usually means your reaction hasn't even started yet. So usually means reaction has not started. Okay? Or that you have no products in this reaction, right? I mean, either way, the reaction has not started. If you have reactants and no products, reaction has not started. Therefore, your equilibrium is 0. And that's the only way that you can have an equilibrium at 0. So once you figure out what these KEQ values are, okay, what these equilibrium constants mean, they do actually give you a lot of information about the equilibrium itself. And that's what we'll take a look at next class. We'll kind of see through graphs and through calculations how these equilibrium constants play out. Alright, that's it for me. I gotta go, maybe do some shopping, and hope to see you guys next time. Bye!